Look here, overlapping takes place in a particular direction. That's what I told you. So overlapping takes place in a particular direction means when you take s orbital, it can overlap in any direction, no problem with that. But px and py, they cannot overlap. So px will overlap with px, py will overlap with py, and pz will overlap with pz. So the direction in which they're overlapping has to be same. So we'll see that examples also. And the third thing, when they overlap, the amount of overlap will be different for different things, isn't it? So in that case, what will happen? The amount of overlap when we are considering, then that gives you the strength of the bond. Some bonds are strong, some bonds are weak. So the strength of the bond depends upon the amount of overlap. Clear? So strength of the bond depends upon the amount of overlap. If the overlapping is more, then the strength will also be more. More the overlapping, more is the strength. Understood? So what will happen? This overlapping continues. More the overlapping, more is the strength. So this point you'll remember. Then the next point which you have to know is when they overlap, they can actually overlap in two different ways. Overlapping can take place in two different ways. So how does it overlap? Now look here. I'll give you. Have you all copied this part? Then I'll go this side. Look here. What happens? Atomic orbitals can overlap in two different ways, which we'll study. I'll show you just now. Atomic orbitals can overlap in two different ways. Now, what are these two different ways that you have to know? Isn't it? In two different ways. Forming. There are two types of bonding. I'll write down forming. Number one, sigma. Forming sigma, that is this sigma bonds. And number two, forming pi. These symbols, you know. So it can form two types of bonding. One is sigma bond, another one is pi bond. Okay, one is sigma bond, other one is pi bond. Is it clear? Any problem? So how these bonds are formed, we'll see the details of these things. Clear? So sigma bond, pi bond. Sigma bond generally is formed between any two orbitals. S can combine with S or P or D, whatever it is, they'll always form sigma bond. But pi bonds, there are certain conditions under which they form. So let's take some examples of this overlapping, and then we'll see how these bonds are formed. So let's see this. Look here. If I take this, then in this case, let's take S and S overlaps. Here, S overlap. So S orbital overlaps with S orbital. Clear? For this, we'll take the example of hydrogen bond, hydrogen molecule. You know hydrogen molecule. What is present in hydrogen molecule? You have one hydrogen and another hydrogen, H2. So there are two hydrogens. This hydrogen, the configuration is 1s1, and this is also 1s1. So the electrons are present in s orbital, and you know s orbital is spherical. So each of them is spherical. This also has one electron. This also has one electron. So I have represented the s orbital. Each one has one electron. Now they have to overlap. This way, these are atomic orbitals, isn't it? These atomic orbitals, they have to overlap. So how the overlapping takes place? This and this, when they overlap, this is your first one, overlaps with second one. So this is your first hydrogen, this is second hydrogen, this is the overlapping space. So you can see this portion is your overlapping space. And in this portion, wherever the overlapping takes place, that is the place where you find the electron. So one electron, two electrons will be found here in this overlapping space. This is a common space where both the atomic orbitals are present. So in that common space, both the electrons will be present. Understood? So when I take this here, what will happen? The hydrogen of this one, this is a hydrogen atom, so this is a nucleus. So this is a hydrogen nucleus, this is another hydrogen nucleus. In between, there's a overlapping. I'm just representing it. This is your overlapping. So hydrogen nucleus is this one, this is a hydrogen nucleus, isn't it? In between the two, there is some overlapping taking place. So in this case, if I join the two nucleus, if I take a line like this, then this line is joining the two nucleus. So this line is called internuclear axis. Internuclear axis. And if you see it properly, the overlapping is on the internuclear axis and in between the two nucleus. So overlapping is on the nuclear axis and in between the two nucleus, isn't it? The overlapping is on the nuclear axis and in between the two nucleus, and hence whenever this happens, straight away overlapping, nothing to do here. This type of bonding, we'll call it sigma bond. So between hydrogen and hydrogen, what type of bond is formed? It's a covalent bond, but that covalent bond will classify it as sigma bond. So this is an example of sigma bond. So this sigma bond, generally in normal case, we write it like this, H dash H. So this is a sigma bond. Understood? S is combining with S. So what is it forming? It's forming a sigma bond. Then SS is this one. It's not necessary. It has to be between S and S. It can be between other orbitals also. So what will happen? S does not have any direction. So S can overlap with P. So we'll now see SP overlap. So overlapping between S and P. How does it occur? The overlapping between S and P. Clear? So to take this overlapping, what will happen? We'll take an example again. We can take HCl molecule. HCl molecule. So in this HCl molecule, you have a hydrogen and you have a chlorine. So hydrogen and chlorine, you have to know the configuration, isn't it? So hydrogen, just now you have done, it is 1s1. No problem at all, isn't it? It's simply s orbital, and here chlorine is 17. So 17 means 1s2, 2s2, 2p6, 3s2, 3p has 5 electrons. 3p, 5. Isn't it? So when I take this 3p5, then in this case, what will happen? Look here. All these are filled up. S, S, P, S. This portion are filled. So we can leave out them because only the unfilled ones which are yet to fill, they will take part in bonding. So what will happen here? These all are filled up. We have left it. What is left? 3p5. So P has how many directions? We have already done. P can be written as this. So this is Px, Py, Pz. This is 3p. Only the 3p part we have taken. The rest are filled up. So we are not taking that. Only the 3p part we have taken. Understood? So when I take this 3p part here, what will happen? How many electrons are there? 5. That means 1, 2, 3, 4, 5. We are filling up the electrons. In filling the electrons, we are using Hund's rule. First, one electron in each, and then it will be paired up. Isn't it? So one electrons in each one, and then fourth one, fifth one. So what is left? Only one electron is left unpaired, and that electron is in PZ. That means, P is dumbbell shaped. So suppose I say this is PZ. That means this is your Z axis. Suppose then PZ, suppose this can be Y axis. So this is Z axis. And here what you have this S does not have any direction. So for S, it is not a problem, isn't it? For S, you don't have any problem, but for P, there's a particular direction. So what will we do now? This has to overlap. Now when it overlaps, you can see these things. What are they called? These are the lobes. So when it overlaps, it will overlap with any one of the lobe. It won't overlap with both. It will overlap with any one of the lobe. There are two lobes. Any one of the lobe will overlap. So either this one or this one. There's no restriction there because both are exactly same. So either this or this. So when it overlaps, suppose this side is overlapping. Excuse me. Suppose this side is overlapping. So what will happen? This will overlap with this. S, no direction. So for S, no problem. P has overlapped in this way. So what will happen? This is your common zone now. So in this common zone, this will be your electrons. So electrons are present here. What about the other lobe? The other lobe will be there, but you'll see it will be represented in a smaller size. Both the lobes were equal. Why they are equal? Because the probability of finding here and here was equal. There was only one electron. So both the sides, the probability was equal. Now it is present here. So the probability of finding electron on the other side is less. And hence, what will happen? The other one, you'll see it is smaller. Is it clear? So this way the overlapping takes place. Any one of the lobe will be used. Understood? So when I take this, then in this case, what is happening here? This is hydrogen, so I can write down hydrogen here. This is chlorine, so I can write down Cl here. This is the overlapping in between. So overlapping is again here. And this lobe is still there, but that is a small one. So this is how we represent. So this one, again, if I draw the axis, what can you say? It is on the nuclear axis and in between the two nucleus, isn't it? Overlapping is on the axis and in between the two nucleus. So what type of bond will this be? This will also be sigma bond. That means if I write HCl, this bond is also a sigma bond. This is also a sigma bond. Understood? All these diagrams you go on drawing. Do I have to wait or I can continue? No problem. Hurry up, you all, hurry up. Finished? Okay, if you are finished, we'll continue. This was SP overlap. S overlap we have seen, SP overlap we have seen. S did not have any direction. So either way they are combining, it is not a problem. Isn't it? For S, direction does not matter. So now we'll see some other overlappings where both of them, they'll have a direction. So let's take P overlap. We are taking P overlap. So how does this PP overlap take place? For this, again, we'll take an example. Let's take easy ones only. Chlorine molecule. If I take chlorine, what will be there? Two chlorines will be there, isn't it? So you have a chlorine here, another chlorine here. Each chlorine, how many electrons? You know, they are 17. Just now we saw the configuration is 1s2, 2s2, 2p6, 3s2, 3p5. By now, you should have learned how to write this configuration. So all this we don't need. We need only p. So p means just now we had seen px, py, pz. So 1, 2, 3, altogether 5, isn't it? 4, 5. So these two are also filled. We don't need. What we need is the unfilled one. So pz is the only unfilled. So here also you have pz. Here also you have pz. So let's take the first one. This is your z-axis. Same way this one also has z-axis, isn't it? Y-axis may be there, y-axis is not used. Px and py are completely filled up, so we don't have to worry about those two. Isn't it? So if I take this, what will happen? Again, this has two lobes, this also has two lobes. So both the lobes won't be used. I have told you, whenever they are overlapping, only one of the lobe is used. So that lobe What will it be? Either it can be this or any one of them. Yeah. So suppose this overlaps with this one. So this is one chlorine, this is another chlorine. The other side will become small because the probability there will be less. The electrons will be present here, isn't it? That means this is a chlorine, this is also a chlorine. In between what you have, the overlapping, this part is small, like this way. Again, I can draw the axis. What will it be? The overlapping is in between the nuclear axis. The overlapping is in between the nuclear axis. This is a nucleus, this is a nucleus. So in between the nucleus and on the nuclear axis. So usually we write Cl dash Cl. This is also a sigma bond. So chlorine is also an example of sigma bond. Chlorine molecule, sigma bond. Done. Have you all copied? Now, PP overlap. We are talking about PP overlap, isn't it? PP overlap is not this much only. What will happen? This was only when one of the P was empty, but it's not necessary only one P will be empty. The other two, PX, PY is also there. So if PX or PY, one of them more is empty. Suppose instead of one, there can be 2 or 3 unpaired electrons. Then what happens? So we have to see those now. Okay. So this one finished, all of you. Have you all copied? If you have copied, then we'll go to the next part. Finished? Then
Yes, sir, copied.
so next. We'll see some more PP overlap, but now the PP overlap will be between two of the P's, not only one P, but there'll be two P's. So let's see how it happens. Clear? So we are talking about this. Look here. We are still in PP overlap, but this PP overlap is of a different thing. So let's take oxygen molecule. We are taking another one, but this molecule is now of oxygen. So oxygen molecule, how does it overlap? Isn't it? So oxygen molecule contains oxygen and oxygen. Oxygen has how many electrons? 8 electrons each. The first one has 8 electron. The second one also has 8 electron. So this 8 electron will become this one, overlapping will take place. So how it overlaps? For that electronic configuration, 8 means 1s2, 2s2, 2p4, 4, 5, 6, 7, 8. So altogether 8. Out of this part is filled, so we don't need that. What we need is 2p4. So p means this one. Okay, I can draw. P is this. This is px, py, pz. It is 2p. Then how many electrons here? 4. So first one, second one, third one, fourth one. So we have filled all the 4 electrodes, isn't it? Now these electrons, how many are unpaired? Py and Pz. So there are 2 orbitals which are left unpaired. So those 2 electrons, how they are going to combine now? Here 2 electrons, here also, since it is oxygen only, same thing will happen here also. That means in the first case, what you have it like this. This is your 2 orbitals. This is, one is Pz, another one is Py. Clear? Now always remember here one more thing, Px, Py, Pz, when we are saying, they are directed along x-axis, y-axis and z-axis. So this x, y, z axis, they are just imaginary. Remember that. I can write x, y, z any side. The only thing is they have to be perpendicular to each other. They have to be perpendicular. So if I take this as your y-axis, then this will be your z-axis. I can take this as z because we have taken the previous one this as z. So let's take this as y-axis. So here also you have this z-axis and then you have this y-axis. Isn't it? Now these two, what will happen? They have to overlap. I have told you Px will overlap only with Px, Py with Py, and Pz with Pz. So here, what will happen? You have Py and Pz. Suppose, like, look here, it's not necessary Py will combine then Pz. Any one can combine first, then the other one will combine after that. All are equivalent. X, Y, Z, when we are writing, it's our imagination, I told you, isn't it? That is just to distinguish between them. So when I take this, suppose this lobe overlaps with this. A very simple thing, what we did just now, suppose this overlaps with this, then this will become small, this will become small, you know that. So these are still left. Remember that. One by one I'm showing. So the first one has overlapped, the electrons are here, isn't it? In this you have the electrons, isn't it? First one, they have overlapped. Now the second one also has to overlap. But here you have a problem. The problem is when S has overlapped, not S, when P, Z has overlapped, it was directly overlapping. Straight away it is overlapping. But once this overlaps, these two, now can they change their position? No, they cannot change their position. They cannot move now, isn't it? Once PZ is overlapped, PZ has already overlapped. So these two cannot change their position now. Now, since they cannot change the position, what will happen? They will overlap in this manner only. The position cannot be changed. So in this position only they have to overlap. So the first overlap was direct, and the second overlap, what will happen? The orbitals are like this. So the other one will overlap in this way only. That means it will overlap here and here. So in whatever position they are overlapping in the same position. These things are very small, so they are very close to each other. And since they are very close to each other, the upper lobe overlaps with upper one, the lower one overlaps with lower one. So what will happen here? This overlapping was already there. And then these two have to overlap. Directly we cannot show. So since it is a representation, we represent it like this. It's just a representation, remember that. So what has happened? This is your main one directly which has overlapped, and this is overlapping in a different way. The different way was like this. So in this case, only one lobe was involved. In the other case, both the lobes are involved. Both the lobes are involved. So that's why what will happen when you are taking this, then in this case, this is oxygen, oxygen. I can show you here oxygen, oxygen. The middle one, I can represent this overlapping here. So the middle one is this one. Above this and below this, there also is some overlapping, isn't it? The middle one is this one. Above and below, you have some more overlapping. So those overlappings I can show you like this. If I represent it in this way. The other overlapping, I can represent it in this way. It's above and below. You can see I marked it with red. So that is a different overlapping from the middle one, isn't it? So if I take this and draw the nuclear axis, what is it? This overlapping is on the nuclear axis, in between the nucleus. But these, are they on the nuclear axis? No. They are around the nuclear axis, isn't it? So this overlapping and that overlapping are different, and hence they give rise to different types of bonding. So this middle one, as usual, we'll call it sigma bond. Whereas this overlapping, this is for the same two set. This is not two different bonds. This is one bond only. And this we'll call it pi bond. So now we have got a different type of overlapping, and that different type of overlapping, we are calling it pi bond. Is it clear? So sigma bond and pi bond, they're two different things. Understood? Sigma bond, what was it? It was like this way. Look here. This overlapped with this, isn't it? So they are directly overlapping. This is called head to head overlap. They're directly overlapping. So that is called head to head overlap. Whereas in case of pi, they're overlapping like this way. Isn't it? So the overlapping is different here. They're overlapping sideways. So this one, side to side overlap. Or you can also call it lateral overlap. So head to head overlap, both the bonds are, no, only one lobe is involved. Only one lobe of each orbital are involved. Isn't it? Only one of the lobe is involved. In this case, both the lobes of the orbitals are involved. Isn't it? In sigma bond, head to head, and only one of the lobe is involved, means one of the lobe overlaps. In case of pi bond, what will happen? It is side to side overlap, or you can also call it lateral overlap. And here, both of them, both the lobes are involved. Understood? So two different types of bond, distinctly two different types, because the overlapping is different type. Here, the overlapping itself is different, so the bond is also different. Understood? So oxygen, how many overlaps are taking place? Two overlaps. So we write like this. So out of these two bonds, whenever there is a multiple bond, one of the bond will be sigma, other one will be pi. It cannot have more than one sigma bond. Direct overlap, only one can take place, isn't it? All others, whatever more bondings are there, they cannot be head-to-head overlap. So that has to be lateral overlap. That means that will give rise to sigma bonds. Understood? So you have sigma bond also formed here. Pi bond, I told you in the beginning, they are on the nuclear axis and in between the two nucleus. Whereas pi bond, sigma bond on the nuclear axis in between the two nucleus. And pi bond, they are around the nuclear axis. They're not on the nuclear axis, they are around the nuclear axis. So they don't touch, but they enclose the nuclear axis. Is it clear? So this is an example of pi bond here. So whenever multiple bonds are formed, then pi will exist. A single bond means only sigma bond will be there. Understood? All single bonds are sigma, but if it is more than one, then pi will come in. Clear? Another example I'll give you is nitrogen molecule. Hurry up. Previous one you all have copied. Hurry up. Finished? Okay, nitrogen molecule, let's see now. If I say nitrogen, there'll be two nitrogens. Nitrogen is how much? 7. So what is the configuration? 1s2, 2s2, 2p3. Isn't it? So 1s2, 2s2. This is filled up. We need only this. So only the p part I'll draw. This is px, py, pz. This is 2p. 3 electrons, 1, 2, 3. So you can see here px, py, pz. All three are unpaired. So what will combine? Px, py, pz. All three will combine. So let's draw it here. This is your px, py is this one. Suppose this is x-axis, then this will be y-axis. Then this is x-axis, this is y-axis. Then what will happen? You'll have z-axis perpendicular. So z-axis is coming out of the paper like this. Clear? It is above the paper. So this is behind the paper, this is above the paper. Same way, another one will also be in the same way. Now, to represent this, it is very difficult on a paper, isn't it? This is your y-axis, x-axis, and this is your z-axis. To show the overlapping, this will overlap with this, no problem. That is head-to-head overlap. But this will now overlap with this will overlap with this. So it is very difficult to show it. Clear? So how I can represent here is, this is px, this and these are combining. So they will form like this. Now, this is there, which is a normal one, and then along with this, another one is here. So two are there. So what will happen here? This will combine with this, and this will combine with this. These are overlapping, isn't it? And then what else will overlap? This will overlap here, and this will overlap here. So there are different overlappings, isn't it? So one was sigma, other two are lateral, so it will be pi. So in this case, what will I draw? Nitrogen, nitrogen. This is your main overlapping, that is sigma. Apart from this, what is there? There's another overlapping just on top of this. And one more overlapping will be there, which to represent perpendicular is not possible because it is above this. So we just represent it here. So I'm just representing it like this, but actually it is perpendicular to each other. So here, what you're getting, this one represents a sigma bond, then this and this represents a pi bond, and same way, these two, they also represent a pi bond. So nitrogen, if I take, has how many bonds? 3 bonds. One of them, we call it sigma, other two are pi. So whenever multiple bonds, one of the bond is sigma bond, and the rest, all the bonds are pi bonds. Hurry up, copy it. Have you all finished? Any problem? Let me know. Hurry up, complete it. Finished? Then we'll continue. Now look here. What you have learned just now is whenever we have a single bond, then single bond will always be a sigma bond. Whenever one bond is formed, that bond is always sigma bond. But if you have more than one bond, then that will always be one sigma, and the rest of them all will be pi. In between two atoms, only one sigma can be formed, but more than one pi can be formed. Clear? So whenever S and S is combining, only sigma. S and P is combining, only sigma. P and P combines, then there's a possibility of sigma as well as pi. Can a pi bond be formed by itself? No. Only one pi bond cannot be formed. Unless a sigma bond is formed, pi bond cannot be formed. Understood? So this thing, you'll remember it. Is it clear? So nitrogen molecule you have done, oxygen, so many you have done. I'll just give you a few more here. You know, we had done this in class 10 only. If I give you this you have done. So what is here? How many bonds are there? You can see 1, 2, 3, 4, 5, 6, 7. So 7 bonds are there, all are sigma bonds. All 7 bonds are sigma bonds. But if I had given you this, then how many bonds? There are so many bonds you can count there. 6. Out of this 6, what will happen? These all single bonds are sigma. Out of these 2, what will happen? One is sigma and one is pi. So if I say this is sigma, then this has to be pi. So 5 sigma bonds and 1 pi bond. 5 of them are sigma and 1 is pi. Isn't it? You also have done this. So what will happen here? These 2 are sigma only. What about this? This will be a sigma bond. This will be pi and this will be pi. So how many? 3 sigma bonds and 2 pi bonds. So different molecules, different number of bonds you can get. Is it clear? Any problem? No. Okay, then we'll continue again. If I take this sigma and pi, what is sigma and what is pi, you know it now, isn't it? So let's distinguish between them. So sigma bond and pi bond. Just distinguish between them. Sigma is this and pi is this, that you know. So what are the point of differences? Just I'll write down the points very quickly. You take a sigma bond. When is it formed? You know it. Sigma bond, it is head to head overlap. And pi bond, side to side overlap, or lateral overlap. Side to side overlap or lateral overlap. The second point, I've told you, when can they be formed? Whenever sigma bond is formed. This is overlapping on the internuclear axis and in between the two nucleus. Overlapping is on the internuclear axis and in between the two nucleus. Here what will happen? Overlapping around the internuclear axis, around the internuclear axis and in between the two nucleus. This is also in between, that is also in between, but one is on the axis, other one is around the axis, isn't it? I've told you only one lobe overlaps. Here, both the lobes overlap. Isn't it? The next one, what will happen? This is formed between SS, SP, PP overlap. Isn't it? SS, SP, PP. All this will form sigma bond. Here, formed between PP overlap after the formation of sigma bond. Unless a sigma bond is formed, a pi bond cannot be formed. Out of these two, which will be more stronger? Sigma or pi, which will be more stronger? I've told you the strength of the bond depends upon overlapping. So which one overlaps more will form a stronger bond. So sigma and pi, which will overlap more? Which will overlap more? One is direct overlap. So direct overlap will always be more than the other one. Isn't it? So what will you see? sigma bond, the amount of overlapping is more. Okay, so here what you can say, amount of overlapping is more, hence sigma bonds are stronger. In this case, amount of overlapping is less, hence are weaker. They are weaker than the other one. Amount of overlapping is more in case of sigma bond, and it is less in case of pi bond. Yeah. Then what we can say when they are overlapping, electrons, they are found in a particular space. So generally we refer to it as electron cloud, isn't it? So here I can say electron cloud is symmetrical. Here electron cloud is unsymmetrical. Electron cloud is symmetrical, other one is electron cloud is unsymmetrical. Why? Because here you have only one line on which it overlaps. Here you have two places, above and below, isn't it? Okay, here it consists of only one electron cloud. There's only one overlapping, isn't it? Here of two electron clouds. Why? Above and below. Consists of only one electron cloud, other one is consist of two electron clouds. Is it clear? Then the next point, remember this is a very important point. Sigma bond means one atom, one atom. They are only connected by one single bond. So what can happen? This can rotate freely. They can, the atoms can rotate. If these are the two things, they can easily rotate about one thing, isn't it? So what will happen here? They can rotate freely. But in this case, what will happen? Two atoms, they're connected by two different things. So here, there's no rotation of, can rotate atoms. The two atoms, they can rotate. So what I can write down? Free rotation of the atoms is possible about a sigma bond. And here free rotation of the atoms is not possible. So in one case, it can rotate freely. In other case, it cannot rotate freely. वो नहीं है हम लोग का. Is it clear, all of you? Have you all copied? So these all things you have to know. One important point from here which you have got is sigma bonds are more stronger than pi bonds. That is another important point. Another one is pi bond can be formed only after the formation of sigma bond. And when atoms are connected with sigma bond only, they can rotate. When it is connected with pi bonds, they cannot rotate. These bonds are directional. I've told you why they are directional, because they combine in a particular direction. A particular direction they can combine. In different directions they cannot combine. Clear? So I'll just repeat one more time the main points. Covalent bonds, how they are formed? They are formed by overlapping of orbitals which has unpaired electrons, isn't it? Atomic orbitals having unpaired electrons, they overlap, and when they overlap, they form a common space where the electrons can be present. The orbital undergoes overlapping and must have electrons in opposite spin. Whenever the same orbital is filled, the electrons are in opposite spin. Clear? And the strength of a covalent bond depends upon the amount of overlapping. So these all points you'll remember. Two types of bonding, sigma bond, pi bond. I've told you how they are formed. You should know them. Clear? And the difference between them I've given you. All these things are very important. You have to learn all these things. Is it clear? Any problem, you all? Anyone has any problem? No. Then this much is enough for today, I think. Isn't it? All these things we have completed. Valence bond theory we have completed. Remember that. Clear? Valence bond theory is this much only. We'll see what happens next day with this theory. There are some changes which has to be made. So what are they? We'll see next day. Clear? So the first theory which you have done is valence bond theory. You have come to know about a sigma bond and a pi bond. Clear? So any problem, then let me know. Otherwise, we'll end up the class. Anyone? Some prick? Tanmay, nothing.
No, sir, no problem.